Okay, Assalamu alaikum to all students. I welcome you to today's lecture on deep learning. We are into week number 15, right? And this is likely to be your second last week of the semester. And the good thing is that we are almost approaching the, the end of the contents as well, right? So I hope today we'll be able to complete the content so that next week we can just see some case studies or some other discussion, which will of course not be a part of your exam, right? So I'll show you some case studies in the next, you can say, session. But before that, today we'll be completing this, right? And at 6 o'clock, you also have a optional quiz scheduled. So anyone who missed out a quiz or could not score well, they are welcome to attempt the quiz, right? Even if you already have good marks, you can still attempt it because you have nothing to lose. Either you will stay where you are or you will improve, right? So the only thing that can happen is improvement. There's no possibility that your marks can go down now. Okay. Anyway, so coming back to the technical aspect, if let me just quickly recall you what we were doing so that we can frame today's discussion in the right context, right? So the main topic we were looking at was object detection, right? And within that, we have already seen a complete family, which is like RCNN and then fast RCNN and faster RCNN. Okay, so all of these actually, each of these represents an iterative improvement over its previous version, right? So maybe I'll spend a couple of minutes quickly recalling you what was going on in each of these, right? So, and then that will serve as a preamble for our today's discussion. So if I talk of the first one, it was very basic one, but the first application of deep learning. So what happens that first you apply selective search, which is a computer vision based algorithm, which gives you 2000 windows of different sizes on the image, right? These are called region proposals. So you have like different regions which can contain an object, right? We don't know what object, but they can contain an object. So each of these is separately fed to a CNN separately, right? You resize it to match the input of CNN, you feed it, and then you get a feature vector. Then this feature vector is fed to an SVM to tell you what object it is. And then you have a separate regression module that actually tightens the bounding box so that you know the exact location of the object that you are looking for, right? So we said it's very slow because you have three different trainings involved. You are fine tuning the CNN, you are training the SVM, and you are training the regression model. So three separate trainings. And if I remember, it was taking more than around, I think, 45 seconds per image at test time, which is by no means is acceptable. Okay. So the improvement to RCNN was fast RCNN, in which the difference was that instead of feeding 2000 different, you can say, boxes to the CNN, we feed the image to CNN only once, right? And selective search is still working, it is giving you boxes. But when you have the output of CNN, you map these boxes on the activation map. Okay, I told you that, for example, if you have a box of say 100 cross 100 and you have a downsampling of 10, so that box would be represented by a 10 by 10 box in the activation map, right? So this is where you are gaining. And then another new concept which was introduced was ROI pooling, right? Where you were actually making sure that if the boxes are of different sizes, they all map to the same number of, to the same sized vector, which you can feed to fully connected layer. And instead of having an SVM classifier and a regression separately, you had two branches within the same network. So this part was shared, where one branch is actually doing the classification, the other branch is actually giving you four numbers, which are the bounding boxes of the object that you are looking for. And next, finally, when we discussed, we said that okay, fast RCNN was taking around 2.3 seconds to detect objects on the average in an image. But out of these 2.3 seconds, this was actually 2 plus 0.3. So this was the time of selective search, and this was the time of detection and localization. So you see, now this has become a bottleneck that the whole network is taking only 0.3 seconds. but only selective search is taking 2 seconds. So we wanted to get rid of this selective search. So what we did, we said, okay, this is a CNN, you are feeding an image. So there's a branch which is reusing these weights, which is called RPN, region proposal network. This region will propose network will propose some boxes, some regions, which you project on the activation map, which you are getting from the CNN, right? So the difference was that instead of using an external machinery that is generating the candidate region proposal, FastR CNN was reusing the CNN weights, and a part or a branch in the network was named as RPN, region proposal network, which only tells you that some object can be present in this region, right? Not the class of the object. The class of the object is this part, right? And then there was also a concept of anchor boxes, that since objects can have different sizes and aspect ratios, right? So that's why in the original paper they were using 9 anchor boxes, that for each position they use 9 anchor boxes, and then we had seen non-maxima suppression, and eventually how you end up with the final boxes. So this was, you can say, the 3 models in this family. And towards the end, we started our discussion on semantic segmentation, right? We had done it significantly. And the last thing we were discussing was upsampling, okay, and transpose convolution. This is where I had ended. So let's go back there and let's continue our discussion from there, right? So I have already given you a review of RCN, fast RCN, and faster RCN. Semantic segmentation was something we started where we said we need a label for every pixel in the image, right? So if this is an image, so we need to tell which pixels belong to person, which pixels belong to tree or grass and buildings and so on, right? So if this is the image, what you see on the right side should be the output. But as you can already tell that this is very challenging, because you also need to label your data like that, right? What you expect as an output, the data should also be labeled in the same way. So I had told you that today you have many tools available which are dedicated for labeling only, right? That you can draw polygons or freehand drawing on an image, and you can click and say, okay, all of this region belongs to this class, right? But still, it's quite challenging. So it's not very easy to get a data that is labeled in this manner. But anyways, so this is what we had already discussed, and we were actually discussing this part that uh, if you see semantic segmentation, so you have convolutional layers which are downsampling the first half of the network, and then in the second half you are upsampling, right? So we had discussed that there are different ways of upsampling, like we had seen nearest neighbor, max, and pooling bed of nails, but we said none of these is actually based on learning. Okay, means we are so simply copying fixed values in the unpooling step that we were discussing. So instead of that, for upsampling, we said transposed convolution is something better, right? What is transposed convolution? It is like reverse of convolution. And convolution, you have an input and you have a filter F, and you have 2 parameters, stride and padding. So you get an output, right? For example, if it's for 6x6, so I'm getting an output of 4x4. Now, in case of transposed convolution, you have this, right? And you have to go in this direction. So what you do, you again have this matrix, and you have a filter, but now you have to upsample that. Maybe from 4x4 you have to go to 6x6, right? So I had also shown you these slides, but I'm just repeating them so that we can link with the subsequent discussion, that if I'm doing convolution, right, with a 3x3 filter, so you see it's in, this part, these 9 values, when I place the filter, they are producing this one single value. Similarly, these 9 values, when I do convolution here, I get one single value here. So in each of these cases, 9 values are mapped to one value, right? Because the filter size is 3x3. So you take the dot product and you get one single value, which you write in the output. So this is actually a many to one mapping. Now, when we are going in the reverse direction, then actually what happens is that you have this 2x2 as an input, right? And now you have to expand it to 4x4. Okay, so in that case, what would we need? This 2 will be producing these 9 values, right? Similarly, this 1, it will be producing these 9 values. This 4 is giving these 9 values, and this 4 is giving these 9 values, right? So in that case, what we do in transpose convolution, I'll solve a complete example as well, that in convolution we are taking dot product, but in case of transposed convolutions, rather than taking a dot product, what we do is, let's suppose I have a value 2 and I have a filter like 1 2 3 0 6 7 1 3 2. So if I multiply this 2 with this filter, so what I get a 3 by 3 or 9 values, right? And these values are actually weighted by this 2. Okay, this can be anything. It can be 2, it can be 3, it can be any number. So when I multiply this number by filter, from 2 I am getting 9 values, right? And these values will be learned. So you see now this 2 is mapped to 9 values, and these values are actually weighted by this input. Okay, I'll be solving it in the subsequent discussion as well, a complete example which we were doing last time. Okay, so let me rather solve it right now so that we can discuss quickly. Let me just take the same example. Okay, if you remember, I also told you that when we are doing convolution, we want to compute the size of output. So it was like n minus f plus 2p divided by s plus 1. Okay, so this is what we have been doing previously. And n was input, f was filter size, right? P was padding. So if we do convolution, we get this as an output. But now the problem is reversed. Now what we are doing, we have n and sorry, we have O and we want to find n, right? Because we are going in the reverse direction. So you can simply rearrange this, okay? And say if you know n or know O, what would be the value of n? So you see what you can do, it would become O minus 1 into S, right? Plus F minus 2P, and this is your n. Okay, so we have simply rearranged this expression. Previously, we knew n and we were computing this O. Now we know O and we are computing n because we are going in the reverse direction. So I think I had given you this example that if we don't do any padding and stride is 1 and filter size is say 2 by 2 and my output is 2 by 2. Okay, if I use this parameter, how would it upsample? So if we plug in these values, so it would be like 2 minus 1 into stride is 1 plus filter size is 2 minus no padding, right? So this will become 3. So it means using these settings, if I have an 2 by 2, I can upsample it to 3 by 3. Of course, you can choose some other setting if you want 4 by 4 or something else, but I have taken these because I will be solving it by hand. So that's why I want to keep a manageable size, not a very big matrix, right? So that's why I have chosen. You can choose different parameters. For example, you can choose a stride of 2, so it will become 4 by 4, right? Similarly, you can include padding, so you can actually control what output size you need. Okay, so now let me quickly solve this example. We will take a 2 by 2 filter, okay, and our matrix is also 2 by 2, which we want to upsample to 3 by 3. Okay, so I had solved one such example last time, but very quickly. So now I'll be doing it very slowly. We still have 10 minutes to go, so we can afford that. Okay, so this is my input, say 0 1 2 3. Okay, this is our input. And we have a kernel. So suppose this is our kernel 1 2, this is our filter. Okay, this is actually learned, but since I have to illustrate, so I have given some values here. So this is our kernel. So we want to perform transpose convolution of this with this kernel. Okay, so here I'm using the same parameters which I told you. So my output would be 3 by 3. So let me just make a 3 by 3 empty matrix, and then we'll keep on filling it. Okay, so this is my 3 by 3 matrix. I computed a little while back why it is 3 by 3. Okay, so now what you do, you pick this 0, you multiply this 0 with this matrix. What do you get? All zeros. So you get 4 zeros which you are filling here. Okay, next. you again put this 3 by 3 matrix. Okay, stride is 1. So previously you were filling here. You take a stride of 1, where will you come? Here. So it means you will now start filling from here. Okay, because stride is 1. If stride was 2, then you would be skipping this and filling there. So since stride is 1, so now I come here. I take this 1, okay, and I multiply it with this matrix. What do I get? I get 1, 2, 2, 1. Okay, and next I have to multiply with 2. Okay, now wait, what do we do? Since this row is over, I go to the next row. I pick this 2. And here, since again the stride is also 1 in the vertical direction, so I started here. So with a stride of 1, I will come here, right? Because I am in the next row, so I need to go down. How much I need to go down? Stride is telling me stride is 1. So I'll start filling from here. So you multiply 2 with the kernel, you get 2, 4, 4, 2. Okay. And next we are left with the last one. So we again draw this 3 by 3 matrix. Again, the stride is 1. So the next time I'll be filling from this point onwards, right? I take a jump of 1. So when I multiply by 3, I get 3, 6, 6, 3. Okay, now I have multiplied my input, all the entries in my input with, you can say, the filter values according to whatever stride I selected. Now what you will do, you simply add them together, right? Why we are adding? Because you see this part and this part is common. This 0 is also contributing to these two values, and this 1 is also contributing, right? This is common. Similarly, this situation will appear in rows as well, in other rows as well. Okay, so you simply add them together and you will get these 9 values. So you see we started with this 2 by 2 input, and this is the 3 by 3 output we are getting, where we have upsampled from 2 by 2 to 3 by 3. And of course, if you want 4 by 4, you can actually choose different values of stride or padding, so that you can upsample to whatever resolution you want, right? So this was one example of how upsampling can be done using transpose convolution, right? If there are some quick comments or queries, we can discuss them in the next couple of minutes. Now we move to the last part of this topic, that is single shot detectors, right? And within that, we'll be discussing a very famous detector that is called YOLO. Okay, so let's see some details on what it is. So you see, previously we have seen 3 different models in the RCNN family, and they are all region based. And what is common in these models is that detection of objects is carried out in 2 steps. The first step generates some regions of interest, either using selective search or using RPN, right? Whatever is the case, the first step is that you have some potential regions of interest, and then these regions of interest are fed to a classifier which process them, and it tells you what object is present and what is the bounding box of that object, right? So you can say this is pass 1, this is pass 2. These are two distinguished steps within all of these 3 object detectors, right? When we say single shot detector, so they actually skip the region proposal stage, right? There is no region proposal stage. They directly run over the image, and they give you the bounding boxes along with the class label. So the advantage is that they are relatively faster, right? But a slight disadvantage is that the performance can slightly go down, right? Because you see it's a trade-off between speed and accuracy. So once you are going for speed, definitely you will have to compromise a bit on the accuracy, right? So we'll see at the end of the lecture today how do you decide which object detector you have to choose. But for the time being, when we say single shot detectors, it means we are talking about speed. We are more concerned about speed. Okay. Now, so the model that we'll see is a very famous state-of-the-art model, which is called YOLO. If you talk of object detection in 2020 and you ask someone, what should I try? Then there is a 90% chance that people would suggest you YOLO, right? So it is like the state of the art that you will use today. Okay. So it was originally proposed in 2016, and the idea was to build a real-time object detector, right? When we say real-time, you know that if you have a video is like 25 to 30 frames per second. Okay. So it means when something is real time, the processing should be at the same rate as you are getting the input, right? So if in the input you are getting 30 frames in 1 second, your system should also be able to process 30 frames in 1 second. Otherwise, things will start piling up. And at the end of the day, you will have a long queue of frames which will be waiting for processing, right? So the initial you can say version of the YOLO, it could process more than 30 frame per second, right? It could process 45 frame per second, and later on some enhancements were made, and today if you download the latest version, it would be even more than 45, right? I think it's more than 50 something. I don't know the exact number, but you can check from the paper, which is very good, right? But of course with a slight compromise on the accuracy. Okay, now let's see some technical detail that how YOLO works. Okay, so this is an image of 100 by 100 in which we see two cars. So we want to detect these two cars, that we should get a bounding box, and we should get a class label that there's a car, right? So what we do is we divide the image into a grid, right? In this example, we have divided this image into a 3 by 3 grid, right? Means you have 9 cells. Of course, this number 3 by 3 is very small number, because we are just discussing, actually this number would be much bigger. Okay, so it means we have 9 cells or a 3 by 3 grid within the image. Now for each of these cells, each of these 9 cells will apply classification and localization, and YOLO will predict the bounding boxes and class labels. Okay, so this is the general idea. Of course, I'll give you more details as we progress. Now, the first thing is that how do we label data? How do you associate an object with a grid cells, right? So you see, suppose for this example, we have a grid size of 3 by 3, and we only have 3 classes in our scenario, right? And these 3 classes, maybe we are dealing with roads or highways. So we have pedestrian, car, and motorcycle. Okay, these are the, you can say, 3 classes. So for each of the cell, you will have a label, and that label will be 8-dimensional vector. Now, what are these 8 values? The first value is the probability that whether an object is present or not, right? Because it is possible that in a grid cell, there is no object, this background. So this probability, if it is 1, some object is present. If it is no object, it is background, this would be 0. Then you have these 4 numbers with which you are already familiar. These are the x and y coordinates of the, you can say, object, not the grid, of the object, okay, which is in that grid. And this is the height and width of the bounding box. Okay, so these are the same 4 numbers with which you are already familiar. And then in this scenario, since we have 3 classes, so these are the probabilities of 3 classes, right? For example, C1 is for pedestrian, C2 is for car, C3 is for motorcycle. So if in a grid there is a car, it will be labeled like this, right? Because we have a car, we don't have a pedestrian, we don't have a motorcycle, right? So let's see how the data would be labeled, and that will help you understand the idea. So if we take this first cell, there is no object, right? Because in our case, object is either a car or a person or a bike, right? So what we do, there is no object, so the probability of object is 0. When there is no object, then all rest of the values are meaningless, right? They are like don't cares, because if there is no object, there is no bounding box, right? If there is no object, there is no bounding box, and there are no class probabilities. So the remaining values are only meaningful if the first value is 1. If the first value is 0, then there is no bounding box, there are no class probabilities, so all of the remaining values would be, you can say, don't cares. Now, let's take this example of this grid cell, right? So you see, now it is very much possible that you have an object and some part of an object is in one cell and some part is in other cell. Okay, you see, most of the car is in this grid cell which is on the left, but it is possible that some part of the car is also in this cell. Okay, but what you will do or how you will label data, this is your object. Okay, and you know the ground truth, so you will say where is the center of the object. Maybe this is the center of the object, and center of the object is falling in which cell? In this highlighted cell. Okay, so this cell is responsible for detecting this car, not any other cell. Okay, so this is something that is important, that an object is assigned to the grid which contains the midpoint of the objects, because it is not possible that always complete object is present in a single cell. Object can be across multiple cells, maybe 2, 3, or even more. So when you are dealing with such a situation, you have to assign the object to that grid cell in which the center point of the object is falling, right? So this cell is responsible for detecting this car. Similarly, the center of this car is here maybe, and it is falling in this grid cell. So this cell is responsible for detecting the other car, right? So now if we label maybe this cell, how it would be labeled? It contains an object. So the first value is 1, and that yes, it contains an object. Then you will have the bounding box coordinate of the car, that where the car is lying. And since it is not a person, so it is 0. It is not a bike, it is 0. It is a car, that's why it is 1, right? This is how you will do it. So now you see, basically what we are trying to do, that for each of these 9 cells, we are predicting 8 values. Okay, so it means your final output is something like 3 cross 3 cross 8, right? That you have 8 values for this, 8 for this, 8 for this, and so on. So what we can do is, we can, as a first attempt, a simplified, you can say, version of very simplified version could be that we have an image, a colored image, then we have some convolutional and pooling layer, and eventually we have a tensor of 3 cross 3 cross 8, right? Which is actually with 3 cross 3, because we have 3 cross 3 grid. So you have 9 cells, and for each cell you have 8 values, right? Why 8 values? Probability of object, then 4 values for the bounding box, and 3 for the classes. If instead of 3 classes you have 5 classes, then of course this number would be 10, not 8, right? It depends how many classes you are using in this particular example. So this is, you can say, a general idea. Now, as I told you that we are doing this example in a very simplified way to understand how it works. But practically, you will take a much larger grid like 7 by 7, 19 by 19, and so on, right? And this is an important point which I will keep repeating, that if an object is contained in more than one cell, it will only be assigned to a single cell in which the midpoint is falling, right? And of course, you can reduce the chances of multiple objects in the same cell by increasing the size of the grid or number of the grid, right? Because you see, if the grid size is too big, then you can have 2 objects within the same cell, right? This will cause problem, right? So that's why this has to be chosen smartly, that you do not have multiple objects within the same cell. Now, how do we encode the bounding boxes, right? We have been using these boxes previously as well, but we did not explicitly discuss how do we label them, right? So you see, in case of labeling the bounding boxes, this X, Y, height, and width, they are relative to the grid cell. Now, what does it mean? Suppose this is a grid cell. So we say, okay, this point of grid cell is 0, 0, and this is 1, 1. Okay. And now I have to say, what is the center point of this bounding box, X, Y? So it will be relative to this box. For example, this is my X, which I am drawing here. This is X, okay, and maybe this is Y, okay. So you can approximate, if this is 0, this is 1, so maybe X is 0.4 and Y is 0.3. Okay, so this is maybe XY, and this is 1 because there is an object in this cell. Now, when we say width and height, okay, so they are again relative to this grid cell. For example, if this hole is 1, then how much is this? This width is like around, you can say 90% of this. Okay, this is likely to be 0.9. So you see 0.9 here. Similarly, if this hole is 1, then this height is approximately half of it. Okay, these are just approximate values to give you an idea. So if this hole is 1, then this height is like half of it, so we say 0.5. So you see, these are the 4 numbers that the way we are encoding the bounding boxes, because if you simply give the location, the absolute location in the whole image, it will be difficult for the model to converge. Now you have all the numbers between 0 and 1, so it can easily learn these numbers. And then since it was a car, so we already know that we have 0, 1, 0, because car is our second class, so that's why we have labeled it as 1, and rest of the classes are 0. And like all other algorithm, non-maximum suppression is also applied in this case, right? So the algorithm, if you remember, we pick the one with the maximum probability, which is 0.9 here, and we say, okay, all other boxes which are overlapping with this 0.9 box, we'll discard them. Okay, and then we'll pick the second maximum, which is 0.8, and all those which are overlapping with this, with a certain IOU threshold, will also discard them, right? So it's exactly the same thing which you already know. So eventually, non-maximum separation will help you get rid of the you can say detections or localization which are all referring to the same object. Okay, so just like we did with faster RCNN, we associate anchor boxes with a grid cell. Now, why do we do that? Because you see, if you are trying to detect a person would be something like this, right? Which has height, which is larger than the width. But if you are trying to detect a car, maybe this box is more appropriate for a car, where width is more than the height. Okay, so what we can do is that suppose we associate two different anchor boxes of two different ratios with the each of the grid cell. So now our label Y will change, right? Why it will change? Because I will have two boxes. For box 1, okay, for one grid cell, we are talking about one grid cell. Okay, for this grid cell, I will have whether this box contains an object, the coordinates, x, y, height, and width. And similarly for box 2, I will have 5 values. Okay, why 5 values? One is the probability that it contains an object or not, and other 4 values are the coordinates. Okay, and then these are C1, C2, C3, these are for classes. Okay, since we have 3 classes, so we have this number will vary depending upon how many classes you are using. Okay, so now it means that for every box I have 5 values. Okay, if there are 2 anchor boxes, so I have 2 into 5 plus 3. This 2 is number of boxes, and this 3 is number of classes. Okay, so if I generalize it, that instead of 2 I can have B bounding boxes, instead of 3 I can have C classes. So instead of 2 I can have any number, instead of 3 I can have any number. So I end up with a nice expression 5b plus c. Now what is it? It is actually telling you that b is the number of boxes, c is the number of classes. Okay, so it means for each grid cell you will be predicting 5b plus c numbers, right? We had done this example for 2 boxes, so for 2 boxes it would be 5 cross 2, which is 10, plus 3, which is you can say 13. Okay, so this is how you actually choose number of anchor boxes. And if you are using a 3 by 3 grid, okay, it means I have 5b plus c numbers for this, for this, for this. So for each of these I need these many numbers. So it means that the output shape should be 3 cross 3 cross, previously we were writing 3 cross 3 cross 8. Why? Because for every 3 cross 3 cell we were predicting 8 values. Now how many values we are predicting? We are predicting these many values for each of the cell. Okay, so that's why the total values would be this. And if you generalize it further, that I'm not using a 3 by 3 grid. Maybe I'm using a S by S grid. So it would be S cross S cross 5B plus C. These are all hyperparameters, right? Said what is the grid size, how many classes are there, data set will tell, and how many boxes you are using, you will decide before executing the algorithm, right? So now if we discuss this idea further, we go back to the original version. So the base CNN architecture, which was used in the original paper of YOLO, it was, you can say, with some modifications in the GoogleNet, and it was named as Darknet, right? So this was the architecture of CNN that was used, which is similar to GoogleNet in many aspects, but with some modification, right? So they were feeding an image of, say, suppose 448 by 448 by 3, and eventually, what you were getting 7 cross 7 cross 30. Now let me explain why is it 30 and how this will work. Okay, so maybe it's a good idea that we can do it. You can see on the board, right? Eventually, at the end of the network, you are getting 7 cross 7 cross 30. Okay, so it means you have a grid of 7 by 7. Okay, and for each cell you are getting 30 values. Now, why you are getting 30 values? If you go back to this 5B plus C, okay, they are actually using two anchor boxes. So B is 2, this is 5 cross 2 plus. They are using Pascal VOC dataset, which has 20 classes. So this is actually 20. Okay, so when you do 5 into 2, 10, 10 plus 20, this is 30. So that is why they are getting a tensor of 7 cross 7 cross 30, because 7 cross 7 is the grid size, and they are using two anchor boxes, and there are 20 classes. Okay, so this is the reason you are getting that particular shape at the you can say last layer. Okay, so let's go back there and see. So you see X, Y, width, height, and objectness score. So these are 5 values into 2 times. And then you have class probabilities. This is actually 20 in this case, right? So this is why you are getting that number, which is equal to 30. So now you see, let's now discuss this 7 by 7. So you see, when we say we place a grid of 7 by 7 on the image, so actually we are not doing it. What actually we are doing, we are passing it to a CNN, and eventually the last volume that I get, okay, means what I get at the end, it is 7 cross 7 cross 30, okay, which is shown here. So if I pick this one cell from here, okay, so this cell is corresponding to this region. Okay, similarly, if I pick some other cell, it is corresponding to this region. And for each region, I have how many values? I have 30 values. I have 30 values associated with each of the region. Okay, so please do remember that when we say we are placing a grid, this is only for understanding purposes. Actually, we are not placing any grid. Actually, what is happening? We are passing our image through a CNN, and due to downsampling, eventually my spatial dimension is 7 by 7 and my depth is 30. Okay, so when I map this image to 7 by 7, if I pick one value from here, so this one single value in this 7 by 7 matrix is corresponding to this region. Similarly, there will be some other value which is corresponding to some other region. So in total, I have a matrix of 7 by 7. It is like placing a grid on this image. Okay, so when I started our discussion, we said we place a grid, but actually physically we are not doing it. Physically, when we pass it through CNN, whatever is the spatial dimension of the last layer, that is actually your grid size. Okay, but this is important, so please keep in mind that we are not doing it actually. There is no physical grid that you are placing. Okay, now let's see an example. And you must have already guessed the limitation of YOLO, that in the version we have seen, each grid cell can predict only one object, right? This is a limitation. For example, if in a single grid you have two objects, then this version of YOLO will not work, right? This is a limitation because the way we have developed, we cannot detect multiple objects which are present within the same, you can say, grid. Okay, now suppose this is a person, the blue box is the ground truth, right? And where is the center of this blue box? Center of this blue box is this. It is falling in this yellow cell. Okay, so it means that this yellow cell is responsible for detection of this person. Why? Because person has a ground truth box which is in blue. The center of that box is falling in this cell which is highlighted in yellow. So now this cell, this particular cell, grid cell, is responsible for detecting this person. Now suppose you run the algorithm, right? You have two anchor boxes, so you get two predictions. Okay, these two blue boxes that you see, these are two predictions. Okay, and of course we'll keep the maximum one, right? One of the bounding boxes you see is also covering part of the wheel of the bicycle. The other is a bit too, you can say, wide, but it is covering only the person, right? So whatever the probability is higher, you will actually pick that and keep that. So you see, as we said, that there are many limitations of this algorithm, although it is very fast. But one limitation is that in a single grid you can only detect one object. So in this case, if the center of the bicycle and the person are falling in the same grid cell, only one of these objects will be detected, right? Because if they are falling in the same grid cell. And similarly, if the objects are very close, then it is possible that two or three objects are falling in the same, you can say, grid cell, so they will not be detected, right? So this is an application of YOLO to an image where you see these persons are standing very close to one another. So when YOLO was applied, right, so they analyzed that in the corner there are actually 9%, 9 Santa Claus, but YOLO was able to detect only 5, right? What was the reason? The reason was that they were very close. So maybe multiple individuals were falling in the same grid cell, so only one of those was detected, right? So this is a visual summary of how it is working. You have cells, one S cross S, where S can be 7, 3, anything. And for each cell, depending upon how many anchor boxes you are considering, you have coordinates and probability. So these are five values depending upon how many boxes. And then you have 20 classes or whatever is the number of classes. So you have probabilities for each class. So this is going on for one single cell. Okay, so if you have, say, 7 by 7 grid, then you will have these values predicted for each of these, which in our example was set to 30. Now, an illustration from the original paper of YOLO, right, where they are showing some detections. This is the grid, and then you have, you can say, all the potential predictions, but when you apply non-maximum suppression, so you are left with, you can say, these three objects, right? So dog, bicycle, and car. So this is actually from their original paper. Now, if you want to see the exact architecture of the model, it is also available, right? But you can use any architecture. So this is not important. You can use some pre-trained model and fit it in YOLO. So this was the actual architecture with all the hyperparameters, but of course you are free to use any architecture as long as you are using it correctly. Okay, now let's see what I need to change if we need to allow multiple detections per grid cell, right? For example, now in this case, if I draw the bounding boxes of the person as well as the bounding boxes of the car, so you see the center will be falling in the same grid. Now this grid cell is responsible for detecting two objects, but in the version that we have seen, we can only detect one object per grid cell. Now if we want to allow multiple detections per grid, we need to change the way we are labeling data, right? So you see now what will happen. Now, if I am allowing two predictions, so I will allow 8 values for each of the prediction. Why 8 values? Because for one anchor box, I have a probability, whether it contains an object. I have 4, you can say, values for the bounding box, and I have 3 class probabilities. Similarly, for the other anchor box, I will again have probability of object, the coordinates of the bounding box, and 3 class probabilities, right? So if you are aligning, say, 2 detections per grid maximum, then you will have 2 into 8, which is 16. Okay, this is 8 because I am considering 3 classes. If the number of classes is different, then of course this number will change. Okay, so it would be something like that. And if we try to now label this grid cell, which is containing both person and the car. Okay, so this particular grid cell, which is like this, this sorry, anchor box in this grid cell. Well, how I would label it? It contains an object. Yes. Here we'll put some real numbers, which are x, y width, height. And since it's a pedestrian, so this is 1, rest are 0, right? So this part corresponds to this particular anchor box. And then when we take this one, which is the car, so it contains an object. Yes, these will be the coordinates. And then what is the name of the class? It is not a person, it is not a bike, it is a car. So C2 is 1. So now you see, with a single grid cell, now you have associated multiple objects. Okay, so when YOLO was proposed in 2016, right? So it had certain limitations. So it was enhanced in YOLO version 2, which was very next year, right? And then in the same paper, which describes YOLO version 2, they use the terminology YOLO 9000, right? So YOLO 9000 was basically, you can say, more or less similar, but instead of 20 classes, it was trained on 9,000 classes, right? The original one was trained only on 20 classes from the Pascal data set, right? So YOLO, when you see the term YOLO 9000, we are talking about 9,000 classes from this data set, right? And eventually you have further enhancement, which is YOLO v3, and it is very, very fast. It can tackle, I think, more than 50, around close to 60 frames per second, which is very, very good. Okay, so this was some you can say discussion on YOLO. Before we start our discussion session, I'll just quickly show you a few applications, okay, that you can develop, which will require exactly the same machinery that we already know, but will simply change the last layer and will be able to solve many interesting problems, right? Now you see, suppose you are solving the problem of landmark detection. What is a landmark? A landmark is a point of interest in an image, right? For example, we have an image of a face and we want, okay, where is the corner of left eye? Okay, so you can use whatever model you are using, and at the last layer you can have the x coordinate of left eye, the y coordinate of left eye, so you can actually maybe predict these numbers. You can train the model, and then the model will learn, okay, where is the when you feed it with a test image, it will output two numbers predicting the corner of the left eye, right? And you can extend the same idea, that why only left eye? What if I want to detect all four eyes, and we want to detect all the landmarks points on the face, like the nose, the lips, and the chin, and so on, right? So you can extend the same model. You can first have a node which tells you whether this image contains a face or not, right? If the image does not contain face, this would be 0, and then rest everything would be meaningless, so it would be don't care. If it contains a face, yes, then you will have some numbers here. Okay, you will train this model, and eventually once the model is trained, you will feed it with an image. It will give you the numbers which are actually telling you the landmark points on the face, right? So very similar techniques are used in many applications, right? For example, you must have seen augmented reality applications or different filters where you can place like a cap or a goggle or anything on the picture, right? So all of these are actually based on landmark detection, that if you know the eyes, then you can put on the goggles. If you know where the head is, then you can put a cap, and so on, right? So you see, it's a simple idea, but using that you can develop any interesting application. And using a similar idea, you can solve a problem which is called pose detection, right? So you see, in a pose, there are certain key points, right? That, for example, where are the shoulders, the neck, the joints of the knees, and the joints on the elbow, and so on, right? So you can actually choose how many key points in the body you will need. You can label your data like that, and just like you were doing for landmark detection, you can actually train a model that which will output coordinates of each of the key points, and then you can actually solve the pose estimation problem, right? Which is a very common computer vision problem. Okay, now let's try to conclude or wrap up our discussion. So this is a good illustration that shows you the timeline of object detection, right? Of course, we have not seen everything, but maybe we have covered this one, this one, this one, and this one. Okay. So other than that, we also covered semantic segmentation using, you can say, but since that is not object detection, so that's why you don't see it in this timeline, right? And these are all related to object detection. So now there can be, you can say, a query that there are many object detectors. So which one should I choose for my problem, right? So for that, I highly recommend you that if you are working on a similar problem, this is a very good paper, Object Detection with Deep Learning a Review, right? So it is very recent, 2019, means last year. So it actually compares the, you can say, merits and demerits of different object detector. Just like I shared with you a paper which was comparing different CNN pre-trained models, if you remember, right? When we were studying CNN architectures, I shared with you the link of a paper which is comparing different models based on how much parameters they need, what is their performance on the same data set, and so on, right? So this is a similar paper, but it is a review of object detection with deep learning. So it will actually give you a comparative review that if your criterion is performance, where should you go? If this is the speed you want, then which model you should try first, right? So if you are working on a similar problem, please go through this paper. And there's another, you can say, plot that I found, and I found it interesting enough to share with you, that you see on this axis we have accuracy, and on this axis we have speed, that how many frames per second we can process. So you see in terms of speed, YOLO is processing 45 frame per second, right? There's another one, SSD, which we have not seen, but speed is almost similar to YOLO, but its accuracy is high. But you see in terms of accuracy, YOLO is like falling behind, right? So maybe in terms of accuracy, this one and this one, they are very high. So you see faster RCNN, which is trained on ResNet, and this one is on VJG. So you see in terms of accuracy, they are beating it, right? But in terms of performance, you see this is like 45 frames per second when we say in terms of speed, sorry, not performance. And this is even less than 10 frames per second. So if you want to go for real time, maybe you should pick this or this. But if you want to go for performance, maybe this is a better choice. And in between, you have, you can say, a trade-off, which is not too bad in terms of performance. It is almost the same as faster RCNN, but the speed is like 20 frame per second, which is more than 2 times of what you are getting with faster RCNN, right? So, but again, if you ask me what object detector I should use, there's no simple answer to this. You have to see the situation in which you want to deploy your system, whether you want real-time detection or not, whether you want to process every image or not, right? Because in a video, frames are redundant, so most of the content is same. Is real-time detection our objective or not? So to answer all these questions, this is the best resource that you can consider. So with that, we'll conclude this discussion on object detection. And if there are some queries, we have time to discuss those. Thank you.